So it's important to remember that every single mineral fits into a mineral group. So the first mineral group is the group called silicates. And remember, silicates, the structure that's used for the silicates is the silicon oxygen tetrahedron. So for every one silicon, there's four oxygens put together in a tetrahedron type shape. The silicates are the most common mineral group when we're talking about the Earth's crust. So 96% of the crust is composed of silicate minerals. That only leaves 4% left for all the other mineral groups. Also, the silicates are broken down into two particular groups. They're the sialic silicates, and I always look and I see the Al in the sialic. Al to me stands for aluminum. So I know there has to be silicon, I know there has to be oxygen, and the Al stands for aluminum. Now, out of the silicate minerals, sialic dominates with about 85% of all the minerals in the crust. And the aluminum has a tendency to make the sialic silicates lighter in color than the cemantic silicates. So some examples of sialic silicates would be quartz, muscovite mica, and potassium feldspar, or just feldspar in general, typically lighter minerals, lighter color. The cemantic silicates, also very, very rich in silicon, also very rich in aluminum, but I look and I see the M in cemantic silicates, and the M typically stands for magnesium, and wherever you see magnesium, you usually see iron, and they stand for about 15% of the silicate minerals that make up the crust. And cemantic silicates, they're typically darker in color. So examples of cemantic silicates would be your olivine and your pyroxene and your amphibole. So just a little darker in color for sure. Onto the mineral group, we have the carbonates. Carbonate minerals, you will have a carbonate polyatomic ion. So you will have CO3 2 negative in the structure. So you'll always look for a carbon and an oxygen together. The most common carbonate mineral is calcite, and calcite is going to be really, really important in this course. So the formula for calcite is CaCO3, so it's calcium carbonate. You just got to be able to look at a mineral formula like this one, see the CO3, and know right away that it applies to the carbonate mineral group. Now, just something I'd like to say about calcite. Calcite is a very important mineral for this course, and it's also the mineral that makes up the sedimentary rock called limestone, and limestone is going to become a very important rock in this course. Even if you were to take limestone, if you were to metamorphose it under heat, pressure, and hot chemical fluids, you'll get a metamorphic rock called marble. So marble and limestone are both made of calcite, and calcite belongs to the carbonate family. Sulfates, if you remember from Science 1206, there's a polyatomic ion called SO4 2 negative. And so always look for the SO4 in a formula to determine that a mineral belongs to the sulfate group. So there's going to be one sulfur and four oxygens. So an example of a sulfate mineral, just one example I'm giving you here now, is the mineral gypsum. And as you can see, gypsum is CaSO4.2H2O. So if you remember from 1206, this is a hydrated ionic compound, and outside of this course, but all that we need to know is that SO4 is in the structure, so this is a sulfate mineral. Also, another example would be the mineral barite. Barite is BaSO4, so there's that SO4, so we know it belongs to the sulfate family. Just to point that out, barite is used in making drilling mud for when you're drilling for oil and gas wells. Also, I should point out that gypsum is used in wallboard in your house. Another mineral group is the oxides, and you'll know the oxides because you're going to see oxygen, and you're going to look for oxygen with one or more metals. So one that comes to my mind, Fe2O3, and also Al2O3. Now Al2O3 is a mineral called bauxite, which is mined for aluminum, and you can see the O with a metal, and the metal happens to be aluminum. Fe2O3 is Pretty certain it's hematite. If it's not hematite, it's magnetite. But there you can see your oxygen, and the metal in this particular case is iron. Yeah, it is. It's hematite. Okay, so always look for a metal with oxygen. It could be more than one metal. The other mineral group is the halides. And so when I think of halides, I think of anytime that you get a metal, and that metal is going to be with one of the halogens. So when you think about group 17 on the periodic table, you'll think of elements like chlorine or fluorine, and if they're in compound with sodium, potassium, or calcium, which are metals. Halides, think of halite. So halite is what we call rock salt, which is sodium chloride, NaCl, which we've already talked about in this particular course. So in the case of halite, Na is sodium, and Cl is the group 17 element. Sulfides. That's the next mineral group. Now, sulfides and sulfates often get mixed up, but what I often say is look for an O for sulfates. There will not be an O in a sulfide. So it's the same rule as the oxides, except this time, instead of looking for oxygen, you're going to be looking for sulfur with a metal. So if we were to look at fool's gold, like pyrite, here's your sulfur, and your metal is iron. Galena, my favorite mineral, here's your sulfur, here's your lead, metal. Sphalerite, here's your sulfur, here's your zinc, metal. No oxygen in any of those formulas. The last mineral group is just a native element. So they're the ones that we spoke about, whereby the element is the mineral and the elements are not in compound. So, for example, gold is an element on the periodic table, but is also a mineral. Silver is an element on the periodic table, but is also a mineral. You can also get native copper. So copper by itself is an element and is also a mineral. I also pointed out earlier that copper can also be found in compound with minerals. Sulfur by itself, S. Sulfur is an element, sulfur is a mineral. So the rules that we use for identifying or classifying the different mineral groups is what I'm going to go over next. So first we're going to go through the mineral groups that end in ATE. So we'll start with the silicates. So for the silicates, you're always going to look for silicon with oxygen. For the sulfates, you're going to look for sulfur plus oxygen. For the carbonates, you're going to look for carbon plus oxygen. So here's an example of a silicate mineral. The formula looks very complicated, but I'm not going to let that fool me. My eyes target in on the silicon, it targets in on the oxygen, so I know right away it's a silicate. If I look at this one here, my eyes target in on the oxygen, my eyes target in on the sulfur, so I know right away it's belonging to the sulfate family. If I were to look at this one, calcite, my eyes target on the O with the C, and I know right away that it belongs to the for the ones that end in IDE, so that's the oxides, the sulfides, and the halides. For the oxides, you're looking with a metal with an O. Sulfides, metal with S, and halides is going to be a metal with one of the group's 17 halogen elements. So if we were to look at hematite, there's your metal with O. If we were to look at pyrite, there's your metal with S. And if we were to look at fluorite, there's your metal, calcium, with a group 17 element called fluorine. So which is an example of a halide? So if it's a halide, we're going to be looking for a metal with a group 17 element. And there's your answer right there. So in this particular case, fluorine is the group 17 element, and it's combined with a metal called calcium. So that is the example of the halide. This would be an oxide, hematite. This would be a carbonate, calcite, and this would be a sulfate, barite.